Hello everyone, I'm Van Huan Huang from Odrive, a company specialized in cloud-based solutions. Today I would like to present our paper which focuses on protecting user privacy and data security in the context of data sharing by leveraging the blockchain technology. The solution is called Privacy Preserving Blockchain-Based Data Sharing Platform for Decentralized Storage Systems. So I'm going to quickly present some existing storage solutions as well as their advantages and shortcomings. Cloud-based storage services have been widely adapted for facilitating data storage and data sharing between remote users. Users do not have to spend money on infrastructure or system-related maintenance costs while still being able to have access to highly convenient services. However, on the conveniences come at the cost of security and user privacy. Outsourcing data to a cloud provider partially deprives a data owner of the data ownership. Users must rely on the service provider, maintaining the data security and user privacy. In fact, the data confidentiality is often protected by the service provider who is responsible for encrypting outsourced data. If the provider is compromised, the attacker can retrieve the decryption key to decrypt the outsourced data. Due to some unexpected reasons, for example, data censorship, the service provider can block access to data of authorized users. Imagine one day you are no longer able to access your own data hosted on a cloud. Even worse, the service provider can remove all the data related to some specific users. Regarding user privacy, a user has to provide its identity to the service provider for verification before being granted access to the requested data. This, however, needs to the user being traceable in the system. The lack of user privacy enables the service provider to chase on activities of any targeted user or discover the relationship between data stakeholders, for example, who shares data with whom. This is not desirable in many scenarios. Uh, There have been also two distributed storage systems called Freenet and Freehaven. These projects aim at protecting user privacy at the network level while improving the data availability by replicating data over a distributed storage system. The approach, however, lacks a flexible data access management. You cannot restrict access to data already uploaded on the network. Everyone with the data ID can request the data and decrypt it. With that said, we aim at constructing a data sharing platform for decentralized storage network. More specifically, we build a publicly auditable access control layer on the top of IPFS network by leveraging the blockchain Ethereum. IPFS network is a peer-to-peer protocol using content-based addressing technique to enable people worldwide to upload and download data in a fast and safe way. The platform ensures the following security and privacy guarantees. The first one is data confidentiality. Data is normally encrypted on the user side before outsourcing. The encryption mechanism allows an effective key management so that data owners do not need to distribute a new decryption key every time it shares a new data. Our encryption mechanism also supports revocations. It means that every time a user is revoked from the sharing, is no longer able to decrypt data shared in the past. This requirement is known as forward secrecy. With respect to data access control enforcement, to improve the shortcomings of the existing storage systems, in which storage providers can block access of authorized users or remove data associated to some targeted users. In our proposed platform, the service provider has no incentives to do so unless they want to destroy the whole system. This is done kind to the privacy guarantee. More clearly, user privacy is User privacy is fully protected. Data owners and consumers anonymously share data in the system without anyone learning any personal information about them. One cannot say who is sharing data with whom. User unlinkability. This implies the impossibility of linking activities made by the same user. For example, one cannot say whether a user has accessed some data several times or how many data sharings that a data owner has made. The last one is user and data unlinkability. This requirement avoids linking any user with any data shares in the platform. So let me present the overall architecture of our platform. The architecture is composed of three entities: user software, smart contracts deployed on the blockchain Ethereum, and the IP-based network. On the blockchain side, we have two main smart contracts. The first one is identity key smart contracts. This is a global contract deployed once for users to register their identity public keys that are anonymously associated to their real identities. This ensures the data owners about the existence of data consumers in the platform before sharing data with them. Users also have the right to update manage their identity keys via functions supported on the contract. And data sharing smart contract is a data sharing smart contract is created by a data owner to manage the location of the shared data on the IP-based network, and the hidden access control that anonymously indicates who have the right to access the data. The data owner can audit and make changes to the hidden access control list over time. Data retrieval requests or data consumers are registered into the contract. This ensures the transparency and auditability of activity over the shared data. On the user side, a user interacts with four internal components to anonymously share data with others. The first one is data sharing engines. This engine allows a data owner to specify the data consumers with whom it wants to share the data with, and this is to construct the corresponding auditable hidden access control list, which is then stored on the blockchain. The second engine is crypto engine. Crypto engine is responsible for all cryptographic operations in the platform. I is the first one is key manager. Key manager is responsible for storing and retrieving keys from the database in an authenticated way. And the next one is key database. Key database is a secure store of keys on the user side. So I will present in detail the two most important components in our architecture, which are crypto engine and key manager. And then after I will present the workflow of all the operations on our platform, such as data uploading, data sharing, user revocation. Now let's get key manager functionalities. Key manager is responsible for storing and retrieving keys from the key database. In our platform, we classify four types of key, each of which has a public key and a private key. The first type of keys is identity keys, which are associated to the real identity of users in the system. The second one is smart contract keys. A user can have many smart contract keys, but one private smart contract key is allowed to deploy only one smart contract. Ephemeral keys. An ephemeral key is a one-time key used to sign all kinds of transactions except transactions needing to be signed by smart contract keys. And hidden keys. The aim of hidden key is to obscure the identity of participant in a transaction with respect to third parties. This means that attacker cannot identify the user involved in the transactions. I now present all the functionalities supported by our crypto engine. The first one is key generation for all types of keys. The second one is hidden transaction generation. The aim of hidden transaction is to prevent adversaries from observing the users involved in the transactions. For example, for both to send a hidden transaction to Karo, both needs to generate a hidden key belonging to Karo. Both then sign the transaction with an ephemeral key. Only Karo can identify that the hidden only Karo can identify that the hidden transaction was sent to him, and only him can read the content of the transactions. The next functions of crypto engine is for data owner to construct and manage auditable access control list. The list is composed of hidden keys. Only designated data consumers can realize that someone is sharing data with them. An adversary cannot extract any information from this list. I now present our encryption mechanism called ciphertext policy attribute-based encryptions. Technically speaking, in a CPABE system, there is a key distribution center which uses a master key to compute and securely distribute private keys to each user depending on their respective attributes. Let's say we have two different users, Bob and Carol, which has two different sets of attributes. They will receive the private keys corresponding to their own attributes. Now, if I need another user decides to share data with others, before doing so, she encrypts data with an access policy which could be constructed in a binary tree. Also, the attributes of both satisfies the access policy. He can use his private key to decrypt data. Carol, on the other hand, cannot decrypt the data. On our platform, each data owner is a KDC, so that they only need to share private key with data consumers once. However, the existing construction of CPABE scheme requires that the access policy is stored along with the encrypted data, which could reveal some information such as some attributes about related users. To overcome this issue, we built a CPABE with hidden access control from a predicate encryptions. Predicate encryption generalizes many cryptographic encryption mechanisms such as identity-based encryption and attribute-based encryptions. And in our CPABE scheme, we also support revocation to prevent revoked users from accessing data shares in the past. Now, ring signature. Ring signature is the next function supported by our crypto engine. Ring signature is a type of digital signature that allows a user to sign a message on behalf of a group of users. Let's say we have a group of users. Bob now uses his private key and the public key of own group member to sign the message to Ernest. Ernest can only verify whether the signature comes from the group without knowing exactly the identity of the signer. So that's all cryptographic primitives we use in the platform. Let's pass to the workflow of all the operations in the platform. To use the platform, a user first needs to register with the identity key smart contract deployed on the blockchain Ethereum. To this end, the user sends the identity key and auxiliary information to the contractor for registrations. User can also manage and update the key via functions supported in the contract. To start uploading and sharing data on the IPFS network, the data owner deploys a data sharing contract on the blockchain Ethereum to manage the data. The data owner encrypts the data and sends it to the IPFS network. Then the data owner specifies a hidden access control list, which is put into the data sharing smart contract along with the location of the data. Finally, the data owner embeds CPIBE private keys in hidden transaction to send to the data consumers. To retrieve the data from the IPFS network, a data consumer has to prove that it is well included in the hidden access control list. To this end, the consumer signs a request with a ring signature scheme based on based on the hidden key in the list. The resulting signature is sent to the contract and placed in the waiting queue. In parallel, a request is also sent to the IPFS network. The storage node checks the waiting queue and sends data to the consumer. After fulfilling the consumer request, the storage node sends a signal to the blockchain to remove the request from the queue. For user revocation and data encryptions, as soon as a user is revoked, the data owner needs to generate a re-encryption key. This key is sent to the storage network for re-encrypting data. This mechanism avoids data owner from downloading the data to re-encrypt, which is a resource-consuming task. In addition, an anti-revocation update is publicly sent to the contract so that all users except the revoked user can successfully update their private key. So after all that, the revoked user is then no longer able to decrypt the data shared in the past. For the security and privacy of our platform, the platform is proven secure based on standard computational hardness problems. These are computational Diffie-Hellman problem and decisional Diffie-Hellman problem. To evaluate the performance of the platform, we focus on measuring the execution time of our cryptographic algorithms, which are computationally expensive, including ring signature and our encryption scheme. We implement the algorithms on a personal computer with the properties shown in the slide based on the cryptographic library called GPBC. On the blockchain side, we also measure the cost of deploying three smart contracts, which are ring signature, identity key contract, and data sharing contracts. These contracts are implemented with minimal necessary operations, and the contracts are written in Solidity language. The results are shown in the slide. Thank you very much for watching.